In section 1.6, we're going to be talking about isotopes and radioactivity and how they're interconnected. So what is an isotope? An isotope is going to be a variation of a specific element to where it has a different number of neutrons than it normally would. So if we look at the example of carbon, this is the information from the periodic table. So carbon has an atomic number of 6, which means that it has 6 protons and 6 electrons. And it also has an atomic mass of 12.01. So if we round that to a whole number, that rounds to 12, which is our mass number. So then we can take that mass number 12 and subtract 6, our atomic number, and that gives us 6, which is our amount of neutrons. So carbon normally has 6 neutrons. And when we have an isotope, that means that we're going to have a different number of neutrons. So for other isotopes of carbon, we may have different amounts of neutrons present. And that means our mass number is going to change as well. So usually when we have an isotope, they're going to be unstable, although it's not always the case, but it is pretty commonly the case. And if they're really unstable, then that means they're going to be radioactive. So let's look at the Bohr model for carbon. So this is the information that you have for carbon 12, which is standard carbon from the periodic table. This is our Bohr model. So we have our 6 protons, which are represented by the plus sign, and we have 6 neutrons, which are represented by these green circles. And then, of course, these blue circles at the minus sign, those are our 6 electrons. So if we look down here, our information about carbon 12 is that we have 6 electrons, 6 protons, 6 neutrons. So that means our mass number, or the nuclear number, is going to be 12. So that's how we come up with this number, carbon 12. So if we looked at some isotopes for carbon, the information will be just slightly different. So this is our standard carbon 12 that we just looked at. Carbon 13, however, also has 6 electrons and 6 protons, but the amount of neutrons is different. So we have 7 neutrons for carbon 13, and that's reflected in this Bohr model as well. The nuclear number, or the mass number, is going to be 13. So that's why this is referred to as carbon 13. So in addition to being able to look at the information on the periodic table to find the mass number, which is, in this case, would be 12 for carbon. So the mass number equals the amount of protons plus the neutrons. So in the case of carbon 12, we have 6 protons and 6 neutrons, so that means our mass number is 6. But if we look at carbon 13, our nuclear number here is going to be 13 because we have 6 protons, but we have 7 neutrons. So in order to find the mass number, or the nuclear number as it refers to it here, that's going to be adding the protons plus the neutrons. So carbon 13 has 1 additional neutron. Carbon 14 has 2 additional neutrons. So instead of having 6 neutrons, carbon 14 has 8 neutrons. Carbon 14, the 14 there is a reference to the nuclear number, the amount of the particles in the nucleus. In writing this information, it's important to use a standard form. So this is isotopic notation, which is sometimes referred to as using the nuclear symbol or nuclear notation. So we're going to have the chemical symbol, which is just our standard symbol from the periodic table. That's the abbreviation for each element. And then we're going to need the mass number and the atomic number. So the mass number is represented by the letter A, which it shows you over here is equal to the protons plus the neutrons. So that's our mass number. And the atomic number is represented by the letter Z, which is just going to be referring to the number of protons. So let's apply that information to our isotopes of carbon that we looked at a few moments ago. So carbon 12 would be written like this. C for carbon, that's your chemical symbol, your atomic number of 6, and your mass number of 12. So that is the isotopic notation for carbon 12. Carbon 13 would be written similarly. We have C for carbon, 6 is our atomic number, and our mass number is going to be 13 because we have that 1 extra neutron. And carbon 14, again, is going to be written in the same format. C for carbon, 6 is the atomic number, 14 is our mass number because we have the 2 extra neutrons in carbon 14. So you can see all of these use the standard format for isotopic notation, and the only difference between these isotopes is the number of neutrons, which is reflected in the mass number that you see here for A. So what does it mean if a substance is radioactive? It means it's going to be spontaneously breaking down and releasing particles as well as releasing energy. So that energy can be absorbed by other substances that are around that atom that is breaking down. So the atom is going to be really unstable. Radioactive decay is a term that is used to refer to the energy that is being released as the atom is breaking down. So as an unstable isotope is being broken down, it's releasing energy and particles, and that action of energy and particles being released is referred to as radioactive decay. It's the atom that is breaking down and disintegrating, and usually it's going to break down into an element that is more stable, or it may break down into a less unstable form, just depending if it's giving off neutrons or protons as it's breaking down. So radiation is a reference to the energy particles that are being released. So this is ionizing radiation that we're talking about. So it is going to be alpha, beta, and gamma rays. And alpha, beta, and gamma rays are going to be released in slightly different formats and can be stopped by different types of materials. So alpha rays can be stopped by paper. So that means if you had a piece of paper in front of alpha rays that were being emitted, then those alpha rays would not penetrate through the piece of paper. Same thing with beta rays, except for beta can pass through paper, but will be stopped by thin aluminum sheets. And gamma radiation can pass through paper, thin aluminum, but will be stopped at lead. So that's why a lot of materials that are ionizing and release ionizing radiation are going to be contained in lead containers, and that's just as a protective coating. There are a few different scientists that were important to developing the understanding of radioactivity. One of those scientists is Henry Becquerel, and he is credited with discovering radioactivity, although it was Marie Curie who actually coined the term radioactivity. So Henry Becquerel was studying fluorescent crystals and wanted to take them outside, expose them to sunlight, and use these photographic plates in order to show that there was radiation being released. And it turns out that when he went outside to do this experiment, it was a cloudy day. And so he wasn't able to do the experiment. So he took his materials, his uranium, and the metal Maltese cross, and his photographic plates, and he wrapped them up in cloth and basically just stuffed them in his desk drawer and forgot about them. So about a week later, he took the materials out, and he realized that the photographic plate had been exposed, and it had absorbed radiation that was released from the uranium. And so that's what we see on these patterns here. And this is where he laid that metal Maltese cross on the photographic plate as well. Marie and Pierre Curie were also very important to developing an understanding of radioactivity. Marie Curie was actually one of Henry Becquerel's doctoral students, and that is how she came to work with him and to develop the term radioactivity. But the Curies worked together in studying radioactivity, specifically looking at uranium. And they were looking at this pitch blende or uraninite, this mineral, and that's what they obtained uranium from. And they noticed that after extracting the uranium that their samples were still pretty radioactive. And they were able to isolate two new elements, polonium and radium. So they did a lot of work with radioactivity, and Marie Curie actually died from cancer, specifically leukemia, as a result of all of her exposure to radioactive materials throughout her years of research. Her lab journals to this day are still radioactive and are kept in these lead containers to prevent exposure to the environment. Marie Curie was also awarded 2 Nobel Prizes, one that she shares with Henry Becquerel and one with her husband Pierre Curie. So she received a Nobel Prize in physics and also in chemistry, and she's referred to as the mother of modern physics.